So I think more or less more than half of you are here. And we were talking about phase diagram yesterday, and we will just pick up from where we just left yesterday and continue. I hope everybody still remembers what we just learned yesterday. So it will be rather a quick recovery, let's say. So I was talking about how we developed the phase diagram, right? From unary to binary. Yeah. When we talk about binary, there are more features for the binary. So first we talk about the isomorphous binary phase diagram, and then we come to the eutectic binary phase diagram. I think you still remember what's the difference between these two, right? So for the first isomorphous one, we could have 100% soluble solids and the liquid solutions. And when we have eutectic system, like the one you're seeing here, we won't have 100% soluble system or solutions between either for liquid or for solids. For example, in this lead and the tin phase diagram, let me get the laser point. You are just saying here. So you have both a alpha phase and a beta phase, but this kind of solid solution only can last for a very small range when we talk about from 0 to 100% octane added to the lead matrix. And for the large volume of the whole phase, you would have alpha plus beta. So this is not a uniform phase. This is a mixture. These are two phases. Yeah. So we talk about many features about this kind of eutectic system because this is one of the most important systems. And we stopped at the fourth feature or fourth slide I was talking to you. So I tried to plan again a little bit with the animation, so you would see how the kind of different phases are referring to different microstructures. So we started from the liquid purely, and then we entered to a mixture phase that's just liquid plus alpha, so plus here, and so it's liquid and solid solution. It's a mixture. And when you just enter to this region here, so you enter the alpha beta phase, you basically have the transition of your beta, so of your beta from the eutectic point and becoming the eutectic microstructure. So in the end, in your final microstructure, you will have, so of course you have your beta phase, which is the red, that's always there. What you have is also two types of alpha. So you have the eutectic alpha, like as you've just cooled down from the eutectic point, and you also have the primary alpha, the alpha that you get from here. So here you get a certain amount of alpha. So this alpha, or just this round and uniform alpha. So this is a very interesting feature for this point when you have this kind of eutectic microstructure in your material. So there are still two phases. So there's still alpha and beta, but for the alpha, you have two types of alpha. So this is a key point for you to just remember. Of course, if you just want to calculate in the end how much alpha we have and how much beta we have, you can always use the lever rule, right? You can use, if you're calculating the weight fraction about alpha and beta in the end, afterwards you just use this R here, you use the S there. So you will get, for example, you will get the alpha weight fraction by just R divided by R plus S. And if you want to get the the alpha fraction, you're going to use just S divided by R plus S. Then you get your overall volume fraction or weight fraction of alpha and beta phase. Just remember the alpha here includes both type, yeah, this primary and also this eutectic alpha. And we will just practice a little bit later on this point. This is a very important point for you to understand. And here I want to just introduce you two interesting concepts or two interesting regions in the phase diagram. So we talk about the eutectic point, and I just discussed with you, if we just go a little bit left to the eutectic point, what you will get, the microstructure you will get is, I'll play everything, you will get that one. So you get this primary alpha, and you also get your eutectic alpha because you have more alpha than beta in the end. So this part from the eutectic temperature composition to, so remember, not to the most left, so to the point where you just stop your alpha phase. So when you go further here, you will unfortunately not have any eutectic microstructure anymore. So you will have a regular alpha beta. It is only valid when you don't enter this region. You stop right here, and at this region, you will always have a feature like that. You will always have a mixture type of alpha primary plus eutectic. And for this region, we call it hypoeutectic. I think everybody knows what hypo, this prefix means. Yeah, that means under. So it's under eutectic, so to the left. So very easy to understand. Then we have the hypereutectic, the same concept. And so hyper, I think you know hyper means over, yeah. So that is over the eutectic composition. And similarly, you will have also something called this primary beta, let's say. And this will be just existing in your phase as a round kind of beta, in addition to your eutectic beta phase. Now, I hope everybody got it. That was a easy definition, but there are two new words for you. So hypo and hyper, but they have very good representation in the phase diagram. I think with that, we can more or less conclude what we learned with the eutectic binary phase. So this is another eutectic phase. I'm showing you again. It's a copper silver eutectic phase. It's looking very similar, almost exactly as the lead and the tin binary phase. The only difference is the eutectic temperature and the composition is a little bit different. And to a certain extent, we call this kind of eutectic binary phase as the terminal solid solutions, yeah, or the phase diagram with the terminal solid solutions. What does that mean? That means you have the solid solutions and alpha and beta, so they're at the terminal. Yeah? So you can imagine this, if this is a flight, so you have one alpha terminal, you have the beta terminal, and you're just getting there from alpha to beta. And in between, that's your flight. And this is a common phase diagram that you would have. But there's also a little bit more complicated one. So still copper as the matrix. So we replace the silver by zinc. And this is not the full phase diagram. You can see this is a zoom in of the phase diagram. I'm just giving you the temperature between around 500 to 700, and the zinc composition is from 60 to close to 100. So this is not all of it, because I want to zoom in and give you a emphasis about this, for example, this delta phase. So for example, here you have gamma and you have epsilon, so they're more or less the terminal kind of solid solutions. But in between, you have something else. So delta is another solid solution that exists at a specific temperature and also at a specific composition. So this is something we call it intermediate solid solution, yeah, because they're in the middle. not exactly middle, but there's something in between. So you don't have just the terminal solid solutions, you also have intermediate solid solutions. And by introducing this data, that will give you something more specific or more different than the eutectic reactions or eutectic temperature and the compositions. Because if you just try to recall what eutectic is telling you, eutectic is telling you by cooling and or heating, you're converting your liquids directly to two solids or just backwards. Yeah. So this is the feature about eutectic. And now if we just look at our beta here, when you just cool it down from the beta, gamma, delta here, from delta to below the temperature of delta, you will see the delta is decomposed into gamma and epsilon. So these two are both solid solutions, and delta itself is also a solid solution. So we call this type of reaction as eutectoid. So, eutectoid transformation. And this is just the one solid solution becoming two or two becoming one if you're heating up. Yeah. So as I told you yesterday, eutect means to melt, and oid, I think this is also a Greek kind of suffix, and I think it means a little bit like, yeah. So it is melt-like, so it's not exactly melting from liquid to solid, but it's close. Yeah, so you're melting one solid to two solids. So it's not exactly melt, but like melt. So this is called eutectoid. And this is exactly similar, as the word is suggesting, is similar to eutectic. And vice versa, if we just go to the upper limit, so the top of this delta phase, you would say this is a phase that you get a mixture. So you have the gamma phase, which is a solid solution, and you have a liquid. So if you just cool down from this one solid plus one liquid, and you become one solid, and we call this kind of reaction or transformation as peritectic transformation. So one liquid plus one solid become one solid, or you just go backwards. So if you just heat it up, your solid will be decomposed into a liquid plus a solid solution. So this is something you don't see that often, and we also don't emphasize that too much. But this is one type of reaction or transformation existing in our materials. So here I tried to give you a summary and also some examples, which you have seen or you will see later in the next slides about the phase diagram. So eutectic is something we have already talked about. One very good example is from the lead tin phase diagram, or from the copper silver phase diagram, you would get such a reaction. And eutectoid is a very common reaction that you will just use in the future, and we will use that a lot in the next phase diagram I'm going to introduce you, which is the iron and carbon phase diagram. So this example here is exactly what is happening. So you will see that later. And the peritectic is something you don't experience too much, but you just need to know that it exists, and you will find few examples in your phase diagram if you pay a little bit of attention on that too. Okay. So we talked about terminal solid solutions, we talked about intermediate solid solutions, and now I want to give you a very specific solution. So this is still a solid solution, but because it's so specific, it has got a different name. It is called intermetallic compounds. So it's nothing but a intermetallic, intermediate solid solution. But the unique feature about it is it has a very specific composition. So it doesn't have a range. It has a specific solid solution. So I'm showing you here is manganese and platinum phase, and you could see. So this kind of intermetallic compound, they're just appearing in your phase diagram as a line. So they don't change their composition at all. So very unique feature about this intermetallic compound is if you just heat it up or cool it down, you will see this composition doesn't change when you go from solid to liquid. So this kind of transformation, so you're going solid to liquid, and this kind of transformation is called congruent transformation, meaning a transformation that doesn't involve any change of your chemical composition. Actually, this is the kind of thing you always see in a unary diagram, for example, where you just heat up your water or cool it down, the composition does not change. So this kind of transformation has also their unique name. All right, I think with all that, you have learned all the basic elements of almost, let's say, 80–90% of the phase diagrams you're gonna see in the future. And I'm also introducing you now the final example about phase diagram. And this is also the most often used, the most often seen phase diagram that you will probably use in the future if you are the metallic phase maze. This is the famous iron carbon phase diagram. So I'm showing you here, not the full of it, if you just pay attention. So on the left-hand side, we have iron, 100%, and we're adding carbon into our iron matrix. And we're adding until a limit, here is 6.7%. Yeah, if you just pay attention here, is corresponding to one intermetallic compound, which is called cementite. So this is a specific composition with the 3 iron atom plus 1 carbon. This is a very hard, by the way, in intermetallic compounds. It is much harder than iron. And this is something for you to remember. And if you just take a look at the diagram itself, you could already easily observe we have 2 unique points. Maybe let's say we have how many, maybe we can try to count how many solid phases we have first. Yeah. Let's start from top to bottom. Yeah. Let's try to explore this phase diagram a little bit. So here we have one very small cute phase called delta, which is not used almost at all. So you just know it is existing because this temperature is too high. Nothing is really happening here in our daily life. But it is one phase, one solid solution. And besides it, you have a large solid solution, which is called gamma. So gamma has also got a name. The name is called austenite. Yeah. Many names for you to remember from the phase diagram. And then somewhere we have this kind of appearance of the cementite. So that's the intermetallic compound. And that's our, let's say, the 3rd solid solution. And if we just still go down and we have, let's say, the final solid solution, which is called alpha. So alpha is very common phase that you see in steel. So by the way, the difference between gamma and alpha, they have very different crystal structures. So gamma always has the FCC crystal structure, and alpha has a BCC crystal structure. So they're both just let's say iron atoms with a larger fraction, of course, And of course, you have some carbon in the interstitial positions. Yeah, so for both gamma and alpha. So that's why you have a solution, right? But alpha has a completely different crystal structure than gamma. So that's also their difference, why there are two phases, because they have completely different crystal structures that make their property, chemical composition completely different. And these are the four solid solutions actually you can see from this diagram. And what else? So I have already indicated you have two important points from this diagram. Yeah. So I would say the first one is here. So you probably notice this is the so-called eutectic point because it has the, within this range, it has the minimum melting temperature. So that is the eutectic point. And again, we have another interesting point, which is here. This is the one called eutectoid point. So let me just show you. Yeah, at the eutectic point, you will see when you just cool it down from liquid, the liquid becomes gamma phase, which is here, plus the cementite. Yeah. So these are two solid solutions. And for the eutectoid phase, of course, when you just cool it down from gamma, which is the austenite, and it will become alpha plus cementite. So it's right here. I was looking for it. It's right here. So that is the so-called eutectoid reactions. I think everything up to now should be clear. If not, just ask. Yeah, unmute yourself. I will not ask you. If you have any questions, just ask. I think they're involving many unfamiliar words, but the concept is rather simple. But if you have problems, don't hesitate. Yeah. All right. So I think with that explanation, you should be more or less quite familiar with this phase diagram. So iron carbon phase diagram. Now we're going to talk about some interesting features because we always want to know for these different phases, what is their difference in terms of microstructure, right? We will specifically focus on the eutectoid part because we have already spoken about eutectic with this lead and tin phase diagram. So for the eutectoid, let's just start with the rather high temperature. Let's say here, it's around about 900 degrees C, where you have a very uniform gamma phase. So you only have gamma grains. And when you just cool it down, similar to what you got from eutectic reaction, for the eutectoid, you will also get such a microstructure. You will also get this laminar microstructure. So you have the alpha plus cementite, just layer by layer. So they're completely controlled by diffusion. Yeah, this is the choice of nature. So when you diffuse your carbon from one place, so you know the alpha phase has very little amount of carbon because the solubility is rather low here, but the cementine has high. So the carbon basically, when it's here, it goes from one place to another, and this higher concentration becomes cementite, and the lower concentration automatically becomes alpha. So this is the driving force or the creation of such a laminar microstructure of your gamma plus alpha plus cementite microstructure here. And it looks like this if you just put it into microscope, exactly like what we draw schematically here. You have layered structure. Of course, when you change the grain, so this is one grain, obviously. When you go to another grain, you have another orientation about this layered structure, but generally it's just layer by layer. And because it is such an important phase, it's not a phase. It's not a phase, by the way. You have to be clear here. This is not one solid solution phase. but because it's so unique, yeah, we also gave a name of it. It's called pearlite. So it feels like it's a phase. For example, we talk about ferrite, we talk about austenite, but you need to understand they are really one phase. They're really one solid solution. But for pearlite, you often call it a phase as well. But in the end, it is not a phase, it is a mixture. So this is something you have to be clear with. So you say it as a phase, but deep down you should know it is not a phase. It is a mixture. Yeah. So I hope you can get there. So it's very difficult for people studying this at the beginning to get there. When you just use it more and more often, you will understand. So we call it pearlite as a phase, but deep down it is not a phase. Yeah? It is a mixture. So I just am telling you the final conclusion. And I think after 2 or 3, 4 years, you will be there and you will remember my bachelor professor told me ferrite, the pearlite is not a phase, it's a mixture, but we call it a phase. Okay? And this is it. So this is the pearlite. And it has this alternating soft ferrite plus very hard cementite. All right, so it looks beautiful. I think you also agree with me. Good. Then similarly, we will explore a little bit if we just go left-hand side, when we have this hypoeutectoid steel, what will happen? So let's see what the microstructure will look like. So we start from the gamma again, as you know. And when we just enter the two-phase region, so this region you would have what? Gamma plus alpha, right? When you enter this mixture region, you will get your alpha phase slightly nucleated. So you can see this alpha is nucleating here, and the gamma will remain there according to the level rule. And at the final point, before you enter the eutectoid temperature, you have the maximum amount of alpha, and you have also the remaining as gamma. But be careful here. The gamma here is exactly at this eutectoid position. So when you just continuous cool down, what will happen? The alpha will not do anything. The kind of already generated alpha, they will not do anything. They will stay as they are. But the eutectoid gamma will just start to decompose it to so-called pearlite. So that's exactly what you're seeing here. So you have all the gamma becoming pearlite. So pearlite is nothing but alternating alpha plus cementite. All right, that's the microstructure you will see here. And once again, I'm giving you an example as you really see from the steel. I mean, of course, under microscope. Yeah. By the way, this is a steel you always see made for the railway. So when you just go with the train and you notice the railway is made of this type of steel. So the steel with really a lot of pearlite. And if you just take a good microscope with you, probably you will see something like this, you know, on the railway. And how it looks like. So you have pearlite, as you have seen here, the beautiful pearlite, alternating microstructure. And of course, you have this new white thing. So what are this white? So the white is exactly this kind of alpha, this kind of ferrite that you got before the eutectoid reaction. That's why we call that pro-eutectoid ferrite, because you also have the ferrite in your pearlite. Yeah. So in the end, you have still two components, let's say ferrite and cementite, but you have two types of ferrite. Yeah. The ferrite in pearlite and the pro-eutectoid ferrite. So they look, I mean, their composition is the same, but they look completely different. Yeah. I hope everybody is still with me. I will not ask you now, but I guess you get the point. This is a point that you easily gave up with material science and engineering. I have to tell you, because all the parts you have learned is interesting. It is well connected to your high school chemistry, your high school physics, mathematics. But this point is really deviating from all that. You don't find interesting equations. You find some weird diagram that you have never seen, and you find some concepts or rules you don't find in practice, in reality. So this is a point you can easily give up. I have to admit that was a point I gave up when I was studying material science and engineering at your age. But this just repeatedly comes, yeah, when you just continue with your master or continue with your doctoral study or continue with your career in business in this field, you will see this coming one by one, so in the future. So don't really feel it is so boring. It is indeed interesting when you really try to apply them in reality, because the concept itself is very simple, yeah, and it is also very interesting to know what is really going on. Okay. So once again, if you have questions, now you can just always ask. And what I'm going to show you now is something a little bit interesting, is doing some mathematical calculation at least, but they're still very, very simple. Yeah. We already know in this final hypoeutectoid steel, you would have pearlite and ferrite. So these are two kind of phases. And but deep down you have what? You have ferrite and the cementite. Yeah, this is confusing, but I think you get these 2 points. Yeah, and your interest in knowing what is their fraction. Yeah, let's go through that. So first of all, you start with this first kind of phase transformation or so. You're getting your alpha and gamma phase right before you enter the eutectoid temperature. So here you have alpha, you have gamma. So how do you want to calculate the alpha phase and gamma phase? So you get the small t and the small s, and you can calculate your alpha phase is this s over r plus s, and the gamma phase is just 1 minus alpha, weight fraction. That was easy. But if you just continuously cool down, of course, you will have your final microstructure, which is the pearlite plus pro-eutectoid ferrite. So I would just call that ferrite, yeah. So it is microstructure between ferrite and pearlite. If you want to calculate your microstructure here, so how much ferrite I have, so alpha phase I have, you're going to use the capital R here and the capital S. So if you just use the level rule, you easily get, okay, I have my alpha is capital S divided by the capital R plus S, and the cementite is 1 minus that. So here, just to be careful, the alpha, what you calculated from this equation, is not the specific alpha. It's an accumulation of alpha. It's the both alpha in your pearlite and the pro-eutected alpha. So this is a very important point. And if you're interested in knowing what is my pro-eutectoid alpha, so what are the fraction of this white one? Yeah. So that's the tricky part, because if you want to know the white one, you have to know the non-white one, right? Because if you just minus the pearlite, what is remaining is the pro-eutectoid alpha, so ferrite. So what is the volume fraction or weight fraction of pearlite? And this is the important part. Yeah, the pearlite weight fraction is exactly the same as your gamma volume fraction, weight fraction, just before you enter the eutectoid temperature. Okay, so this is important point, and I hope you also get that, because it's really pretty easy. but it takes a little bit of effort for you to get familiar with all these terms. All right, that's enough for hypoeutectoid. Now we're moving to hypereutectoid steel. And this is nothing new. It is exactly similar as we just learned. So you just need to pay a little bit attention about the range for the pure ferrite and iron and carbon phase diagram. We're talking about the hyper from 0.76% of carbon to 2.06% of carbon. So, but be clear, this is pure iron and carbon phase diagram. You will see a lot of elements, a lot of features will influence this. Yeah? And we're here just talking about a binary phase diagram. So in this, if it just cool down from gamma, you can already imagine, yeah, you will have what cementite nucleating from your microstructure, and they will just stop by the eutectoid temperature, and they will form the so-called proeutectoid cementites, yeah, the white one. And when you just continue cool down, the remaining or the prior gamma will be just deposited into the alternating alpha plus cementite, which is the perlite. Okay, and of course you can do exactly the same. I will not show you in detail to calculate the volume fraction of the final alpha and the final cementite, or you can also use just the level right before the eutectic point to calculate the volume fraction of, let's say, eutectoid cementite, and also your perlite phase. Okay, I think that should be the last slide about carbon and iron and carbon phase diagram, as I said, which is the most important phase diagram for you for this lecture and also for your future use if you are in steel business. Yeah. All right, I have already mentioned something will influence your phase diagram, and here I'm showing you if you just add a little bit other elements. So here is adding, for example, let's take a look at, for example, titanium, yeah, right here. So if you just add a few titanium in this binary phase diagram, by the way, it will become not a binary, but a phase diagram with the 3 phases. And what it will change. So adding a little bit titanium will elevate your eutectoid temperature significantly. So we have it around, let's say, 700 degrees C, and by just adding very little, this eutectic temperature will become more than 1,000. Yeah. So if you add different elements, they change accordingly. And of course, the composition of the eutectoid will also change accordingly. If you just if you just look at the titanium again here, you add a little bit, the eutectoid composition will change from 0.76% of carbon, decrease significantly to even 0.2%. Yeah. So this is something for you to know. You don't need to memorize all this. Just to have a impression of that, because maybe when you really do something on this in the future, you will see a iron carbon phase diagram completely different from what you learned today. Don't be surprised, because they are changed with other alloying elements. All right, I think it's time for you to have a quick summary about phase diagram. So I think in the phase diagram chapter, I introduced you many concepts about solubility, about mixture, about component, about phase, everything. But the most important thing is for you to know phase diagram is a useful tool to do a few things. You can just get the phase, what phase is present and what is the composition of each phase, and also how to calculate the weight fraction of each phase. So this is an important part about phase diagram. Then I introduced you the binary phase diagram significantly. Started from the isomorphous, then we moved to eutectic, and then finally we moved to the iron carbon, which is both eutectic and eutectoid phase diagram. In those three phase diagrams, I think you learned three important reactions: eutectic, eutectoid, and peritectic. And of course, you learned how your microstructure will develop while you just change different phases. And you also learned the microstructure is strongly dependent on the composition, and it also strongly dependent on the cooling rate. Yeah, we didn't talk about that too much, but if you remember what is equilibrium phase looks like, and what the non-equilibrium, the core phase looks like. So that's the difference about the cooling rate. But anyway, we're still talking about everything in equilibrium. So you now might ask, is equilibrium always maintained? That's not the case. So that's why we're going to move on with phase transformation, because phase transformation is a feature that you have not only chemical composition change according to temperature, but you are also changing your time. Yeah, so phase transformation happens with time. So to reach the equilibrium. So then you easily ask, well, what is the rate? So how much time I need to get the equilibrium? Yeah, that's one thing. So, but if the time is really long, if it's seconds, minutes, that's okay. If it's days, we cannot wait for that, right? So what will form or what will happen if we don't have equilibrium? Is the phase diagram will be useless at that point. And of course, in the end, if we get a phase in non-equilibrium condition, what will be the difference in terms of microstructure from those produced in equilibrium? So I think in the phase transformation, we will just touch those few questions and give you some answers. Once again, after this chapter, what you will learn, what you will be able to do is first, you can make a schematic drawing between the transformation versus time. So you will know how much time you will need to complete your phase transformation in an equilibrium condition. And you will be also to describe some microstructures. So these microstructures are either produced in equilibrium or non-equilibrium. So they include fine perlite, coarse perlite, bainite, something you haven't heard, and martensite as well, and tapered martensite. So these are the new terms you're going to learn today. And after that, you should be able to kind of correlate or cite the mechanical characteristics of all these phases. We want to know for all these different phases, either in equilibrium or non-equilibrium, what their mechanical properties will be. Finally, you will be able to learn when we really want to produce these phases, how we're going to do. So we will use two different ways. One is called isothermal transformation, the other is called continuous cooling transformation. So we will practice these two kind of transformation, let's say, strategies in a carbon and iron diagram. Okay, that's enough for the introduction. So now we start with the phase transformation topic. So first of all, what is phase transformation? So how is phase transformation composed of? We didn't speak this process. We were speaking all the different phases, right, in the last chapter, but we didn't speak how this process is done, because it's driven finally by diffusion. If you remember what we learned yesterday, the phase transformation, most of them is driven by diffusion, your carbon from one place to another. But as we learned, diffusion takes time, right? So that's why phase transformation also takes time, and it has two phases. So the first one is called nucleation, and the second is called growth. So the nucleation basically is to have some seeds. You saw those small crystals or particles growing from liquid from one solid solution. That is called nucleation. And based on this nucleus, you will basically get your atom, your phase to grow. So that is the growth phase. So we have these two phases for the phase transformation. And the driving force for this either nucleation and growth is basically something we didn't touch too much. It's called delta T. So it's either increasing or decreasing your temperature. So you always need this delta T to get your phase transformation triggered. If we just want to do the cooling or do the solidification, we need a super cooling. So you need to lower your temperature a little bit. Otherwise, you would need to wait for such a long time. For example, you want to trigger eutectic reaction. So you know the eutectic reaction for steel, for the zinc, lead and tin binary phase diagram is around 700 degrees C, and you enter that temperature exactly, and you hold. So you will wait for hours, days, months to finally get to equilibrium. I mean, it will happen, but it will take so much time. If you just do a undercooling, if you go below 700, you go to 600 or so, you will just trigger the phase transformation so quickly. So you can see the driving force is this salt delta T. I think everybody has experience in this from your daily life. If you want to cool down your something, you don't just go with a little bit temperature drop. You go very, very low. I will not explain in terms of thermodynamics about this because that will begin another lecture. You just kind of get the sense of it. So the supercooling, in other words, also superheating, will just increase your phase transformation rate. And the feature is if you are applying a small supercooling, you will get slow nucleation rate. So you get that. Slow nucleation rate is referring to very few nuclei. So you will not have so many kind of seeds in your microstructure, but they will still grow. So with this few nuclei, you will basically get very large crystals. Because there are few. Of course, if you're applying a large supercooling, if you just cool it very quickly, you will have a rapid nucleation rate, and that will create many nuclei, and that will lead to small crystals. If you just remember what difference between small and large in terms of mechanical property, you will see what you will need. All right, I think this is a point for us to take a break, and let's come back to the lecture at 11:15. All right. So I hope everybody's back. Now let's continue with our second half of today's lecture. And we just spoke about phase transformation with some definition. Here I'm giving you one example. So how this supercooling is meaning and why they're creating a microstructure as we just described. So this is a so-called, let's say, a casting. So you will learn what that is later on. And what you just see is we have a, let's say, a chamber, and you just pour some of your liquid metal into it. And you would see finally the microstructure is looking in such a fashion. So you could observe, so at the corners or close to the walls, you get kind of a rather small grains, yeah, if you just notice them. So rather small and even quite equal exit grains. And if you just look at it in the center, you have a rather large, so columnar kind of grains in the center. So this is exactly referring to the effects of the supercooling. Yeah, because when we just talk about the corners or the walls, so here, because your liquid exactly in touching with the metal, which is cool, yeah, so you have rather fast or large supercooling. So the delta T is greater. That's why you would have rather small crystals, small grains, and also rather kind of equal exide, because they cannot grow too much. They grow a little and they meet another grain and they become small and equal exide. But in the center, so because the supercooling is low, yeah, it is not touching anything. So you will not have so many places for the crystal to nucleate. Yeah, so that you have rather small, fewer nucleation sites, and that's why your grains finally will grow big. Yeah, so they're much bigger, and you can obviously see they're growing just towards a certain direction. So this is a very good example for you to understand why the driving force for phase transformation is the delta T. So it's either supercooling or superheating. And of course, when we speak about solidification, as you already see from the example, we have two types of nucleation. So the first one is the nucleation pretty homogeneous. This is exactly nucleating from almost, let's say, nowhere. Yeah, just you're in your metal and suddenly you get a nucleation point. So there is a physical motivation behind that, but we're not going to touch about it because that is related to thermodynamics. You will learn according to Heiju next semester, so I hope you will get to understand of that by then. And the second type, which is something we usually experience, is called heterogeneous nucleation. That is the nucleation that you would find at the surface, let's say, because it's much easier, not because the delta T is small. It is also because the energy that required to nucleate over there is much lower. Yeah. So that's why the crystals will be much easier to nucleate. And the supercooling that you need, or superheating, let's say, is pretty small. So it's just a little sum of the degrees. And for the homogeneous one, you need really from 80 to 300 degrees C to get a sustainable solidification process going on. All right, so these are the two types of nucleation. Now I'm giving you already a description about this nucleation rate. So we're not talking about how this is derived. As I said, this relates to really a lot of thermodynamics knowledge, but I'm giving you how it looks like in the end. So in the end, we're describing your rate of phase transformation by this quantity, which is called the fraction of transformed phase. So basically, we're starting from zero, if you're thinking about it, from liquid to solid. So when you're in liquid, you have zero solid. And at nucleation phase, you have really little, yeah, very countable, let's say, nuclei, and they occupy almost nothing in terms of volume or weight fraction. But when you enter the growth phase, you will see some significant increase of the phase that transformed. So you just can kind of characterize this diagram into three stages. So the first is the rate increases initially and a lot. And at a certain point, your rate reaches a maximum. So I'm not talking about the fraction, but we're talking about the rate, so the derivative of the fraction. So you can see the derivative is always increasing at a certain point, which is usually corresponding to half of the transformation. And after that point, you're entering a transformation very, very slow. The rate is becoming slower and until you reach 100% of phase transformation. Yeah. So this is typical behavior for the rate of phase transformation. And of course, the x-axis, I didn't mention specifically, is time. So usually we use a logarithmic version of it because the time is pretty long. And this is a equation to describe this one. I think this kind of curve is something you see very often. Well, we have already seen one yesterday, which is the area function. Yeah. When you describe statistics, it is also having such a curve shape. And today there's another function which is called Avi-Remy function and the equation. It is an exponential and power law combination. And this is also the famous JMAK equation. So A here is standing for Avi-Remy. There are also a few other people who contributed to this equation. And this equation basically is describing the phase fraction that transformed and with respect to time. So this is how it looks like. You could see two controlling parameters are there. One is K and one is N. So I just want to give you a little bit impression how these two parameters are controlling your phase transformation rate. Let's say if we speak about the effect of N, so I'm giving you two expressions here. So the blue one is corresponding to a smaller n, which is 1.5, the exponent here. And the red one is giving you a expression of a large n, 2.9. So you can see that with n, you are really changing the shape of your transformation rate. So this is rather slow, and this is becoming very fast. You can reach the full transformation very quickly. And what is the function of K? So K is a function, also change a little bit of your shape, but it is rather really shifting. So this is the 2.9 with 0.1. That was the blue you just saw. And now I change the K from 0.1 to 0.01. Yeah, so it is becoming smaller. And with that, you can really shift your transformation curve from left to right. Of course, the shape is also slightly changed. As you can see, it is given to the whole exponential function itself, but the shape is not too much. It's rather shifting. So you would have a longer nucleation phase in that case, and reaching also a little bit slower to your final full phase transformation phase. Okay, and a very common use term from phase transformation is so-called average phase transformation rate, or we simply call it phase transformation rate. Yes, the rate is changing, as you can see, it's from here to there. It's increasing and decreasing. But we want to use one scalar. We don't want to use a curve to describe it. That's why we take the average, and the average is somehow related to the rate when you have 50% of phase transformation. So this is also so-called T.5. And if you just inverse it, you will get the rate. Yeah. Because in the end, you're trying to get the whole volume fraction as 1. Okay, so you take the time when you have half of your phase transformation and you inverse it, you get the rate of it. So this is an important concept for you to describe your phase transformation, on the rate of phase transformation. And now let's simply look at some example about this kinetics, about the supercooling or undercooling, let's say, or superheating in terms of phase transformation. This is a transformation we have already spoken about just a few minutes ago. It's the eutectoid phase transformation for carbon and iron. When we have 7 to 7 degrees C, you're getting from gamma phase to your pearlite, so from austenite to pearlite. Yeah, so the reaction is clear. And here I'm also showing you again what is the diffusion behind it. So this is what you can see. You can see those carbon items that is fully dissolved in your gamma. They're just moving from one place to another, and the enriched part is becoming cementite, and the poor part is becoming the alpha phase, the ferrite. Yeah, in total, this is our pearlite. So this is something you have already fully understood. And what is effect of supercooling then? Yeah, so this diagram is showing you the effect of supercooling. Let's say here is our phase transformation diagram. So this is the volume fraction of phase transformation, and this is the time. You can see when we just use a rather smaller delta T, so we cool a little bit down from the 7 to 7 to 675 degrees C. This is what you get with transformation. But if you just cool it further, so you decrease to 650 and even 600, when the delta T is becoming large, now you can see the transformation is reached really fast. Yeah? The full transformation is increased by magnitude. So here you have almost 1,000 seconds, and here you have even less than 10. That's the huge difference. Yeah, but the consequences is when you have delta T large, you of course get some very fine pearlite. Yeah, because the reasons I have given you, you have rather many nucleus, and that will lead very small grains. And if you have rather large, if you have rather small delta T here, right here, and you will get some coarse pearlite. Yeah, they will form at rather higher temperature, and they become relatively soft because finer grains will enhance your strength. Hopefully you still remember. All right, so that's the supercooling in application. Now you have already understand, let's say, at different temperature, we just saw a few different temperatures, you would understand, you would see how our material will take to get a full transformation. Yeah, but how can we just express them? We don't want to always look at thousands of such a diagram. So for each temperature, you can draw a transformation diagram, right? Then you understand, you look up into the diagram. Okay, for this temperature, I need this time to get this amount of transformation. So we want to use a rather simpler way to do this. And what we're going to use is a transformation, so-called this TT diagram. So this is a isothermal transformation diagram. This is the temperature, and this is time. So how do we do this? We basically take one temperature, let's say 675, and we record the time, the time when you start your phase transformation. So you're from zero, from austenite becoming zero, the starting of pearlite. And when you have 50% of it, and you gave another contour, so at this contour you have 50% of pearlite. And when you go to 100% of pearlite, you go to this red one. Now you have 100% of pearlite. If we just do this for all the temperature, so you can imagine in the end, we will just drop a plot, a contour for all the temperatures, and you will know for each temperature how much time you need to complete a certain amount of phase transformation. what you can see from this diagram is also, if you just apply very little supercooling, like very close to 7 to 7, you can see the time that you needed is really almost infinity. If you just go down and down, if your supercooling is bigger and bigger, your time needed to complete your phase transformation is very short, very much shortened. But here I have to give you one question to think about. What if we continue supercool it? Will that be still shortened or something else will happen? You can think about it, because you still need to remember phase transformation is driven not only, it's driven by supercooling, by delta T, but it is a process of diffusion. And diffusion needs a certain amount of temperature as well, right? All right, so that was about austenite to perlite isothermal transformation. And we will go on with this phase diagram to a little bit in practice. So we already learned this diagram, how it is drawn and how it is made. We just use different temperature. So after such a diagram is created, we can basically use it to design our kind of solidification processes. So for example, I have my steel starting from austenite and I want to get full perlite. So you can just, you try to cool it down to a certain temperature, let's say 600 something, and then you just hold it. This is why it's called isothermal transformation. So the temperature does not change. You just hold it and until the time is reached. So for this sense, it's 100 seconds. Now you know, okay, the steel is complete 100% perlite. Now I can just simply cool it down. Now you get 100% perlite. And the microstructure will exactly look like the whole process, from austenite to perlite. And that is something if you have your eutectoid position, but of course, your position could be different. Now we're considering a composition not at eutectoid, but a little bit larger. So in that case, you will not just have perlite, right? You will have a phase where you have gamma plus cementite, so austenite plus cementite here. So that's why you will have an additional curve here, so to indicate this phase transformation of that. So you have your austenite, so A is standing for austenite, and when you just hold a little bit longer, your austenite will become austenite plus cementite. So for example, here we're speaking about something between 700 to 800, it's right there. So if you just hold, okay, you will come to this phase, but something different from the perlite phase transformation. When you go from liquid to liquid plus solid, the rate is much faster. So because there's liquid, right? So you have something like a curve. You don't have the really different volume fraction of cementite. So it comes rather instantaneously. But afterwards, when you go to the solid phase transformation, it will take ages. If you still stay with the 7 to 7. Of course, if you just go down a little bit, you would have very fast perlite in the end. So this is how let's say the isothermal phase transformation diagram is applied for hypoeutectoid composition. And of course, that relates to the question I just asked about you. If we just still do more supercooling, what will happen? That was something between 500 and 600. And now if we just go down to 400 or 400 to 500, what will happen? So you will see something else will happen, because if you still want to get perlite, your diffusion will not allow you. You need a certain amount of temperature to activate your diffusion, right? And here we're going to a phase called bainite, as we are not able to formulate those beautiful pearlites with that kind of temperature, with that slow temperature, although the driving force for phase transformation is still there. But since the diffusion rate is not high enough, sorry, what you will create is a phase called bainite. So they still look pretty similar to, let's say, pearlite, instead of the layered structure. So you have layered cementite and ferrite. Here you don't have that beautiful layer anymore. You have rather elongated cementite. So it will have some kind of discontinuities. So you have, this is the one elongated and next to the other elongated and so on. So it's a little bit looking like, let's say, pearlite, but not exactly. So you also see the pattern is not that good anymore. So this is so-called the bainite. And to be more precisely, we're talking about so-called upper bainite. So because if you go a little bit lower or even much lower, the microstructure does not look like this anymore. It looks like a little bit, again, different, because it will be not easy to formulate even as beautiful as this. So we're not talking about those more microstructure anymore. We will stay with the upper bainite, and this is what you have. And you may ask, so okay, I go down to 6, I go down to 4, 600 to 400. What if I go further down? If I just come from 800 directly to room temperature? Yes, you can do that, of course. And you can do that also with very fast rate. So you can see if we just do such a process, you drop your temperature within very short time. You will enter to a new phase, which is called martensite. And martensite is simply a non-equilibrium phase. So this is the first one for you, which is not created by diffusion even. So that's why it's a non-equilibrium phase. And how it's done, if it's not created by diffusion, how it is done. First, I need to tell you what is martensite looking like. So martensite is a BCT structure, so-called. So it's a structure, so BC is the body center, and T here is standing for a tetragonal. So it's not a cube anymore. So if you just look at your FCC, the white atoms are representing the FCC. So this is a cube if you just look one. So here I'm giving you 2. If you look at 1 cube and you have all the elements or your faces, so it's FCC. If you just apply certain deformation, so either sharing or here we're kind of giving a little bit of extraction here and we're giving a contraction there. So the FCC will be kind of shared in such a way. And it will become a new structure. So this new structure is using a part of the atoms from one FCC are part from the other FCC. You can see if you just look at these black ones, this is becoming a cube-like. So this is not exactly the cube because the height is not equal to the length. Yeah, that's why it's called a tetragonal. But in the center of it, you will use one phase atom to become a body center of your BCT, of your this kind of tetragonal structure. So this is so-called BCT, and this is the crystal structure of martensite, basically. And this is how the martensite is created. Yeah, that's why it is not diffusion driven. It is actually mechanical driven. It's a shear driven process. That's why if you just quench it, if you just cool it down so rapidly, directly to a temperature below the so-called Morningside starting temperature, you will get your Morningside. Yeah. So it also has a contour, but this contour is not a function with respect to time. It is a function with respect to only temperature. If you enter a certain temperature, you will start the Morningside transformation. And if you get a certain temperature, you will finish with a completely Morningside transformation. All right. So this is a typical non-equilibrium phase transformation for Martinsides. Okay. And now we know how Martensite is created and how it looks like. It is basically by a rapid cooling, and we call this rapid cooling with a specific name. It is called quenching. Yeah. So when we just quench the gamma phase, we will get the so-called Martensite. So Martensite has few interesting features. I would like to give you some emphasis on that. So first of all, it's a single phase with body-centered tetragonal BCC structure, and it is diffusion-less transformation by sharing only. So we have already emphasized these 2 points. And that also gives the Martensite some specific, let's say, mechanical property. Because of this sharing, you can imagine that actually is promoted by what? By dislocation. That's why you have quite increased dislocation density in your Martensite instead of this diffusion-driven processes. And due to this diffusion, dislocation density and sharing, you will also have some residue stresses, right? And due to this increased cooling and this whole process, you will also have very fine microstructure. I think you probably noticed in the previous slides. So this is how your Martensite will look like. They're very fine and they're needle-like. So they look like a needle. So it's very small microstructure. That's why you have very fine microstructure. And in the end, it's very hard to get full percent of Martensite. That's why in the curve, you didn't see 100%. You actually see 90% Martensite finishing, because you will always get a certain amount of cementite in your microstructure. Actually, why I'm emphasizing these 3 features here, because all of them, if you remember our microstructure to mechanical property relationship, all of them are contributing to very high strength, all of them. And the consequences of the high strength is the Martensite is brittle. That is also the reason we don't usually directly use Martensite. And we always try to make the Martensite a little bit softer. We want to get their high strength, but we also want to make them softer, less brittle. Then we introduce a new term, it's called tempering. So this is another heat treatment process, and we will talk about in the next lecture. So basically, we're converting the Martensite back to what? To the alpha BCC plus cementite, to the pearlite kind of phases, but not fully. Now, that's why you will get a good strength property of the Martensite. You will also get the good property of the pearlite where you have ductility. So you will get the balanced mechanical property after the tempering. All right, that's all about all the important phases I want to introduce to you. And we will talk about a real process phase transformation. So we were just talking about either isothermal cooling, or we're also talking about the quenching. You can see these are 2 extreme cases. So for isothermal, you just hold at one temperature and wait. And this is okay, but this is not very, let's say, economic friendly, because we don't want to use it so often that you need a lot of time. And you also need energy, right? You need energy to maintain a high temperature for your material. And for the quenching, that is good, something we like because it's fast, but you need to go back to the tempering process and to make your material applicable or usable. So a rather compromises, a rather interesting process is something so-called continuous cooling transformation. So first of all, what is continuous cooling? So this curve is indicating you continuous cooling. This is a curve you usually see. When you just put a hot dinner on your table with air, room temperature, and this is what it will happen. It will just continuously cool down. This is a typical curve of continuous cooling. So with this, you don't need to hold for so long, and you also don't need to get the extra energy to maintain your high temperature. And you can also avoid you really quench it. You will still get a rather useful microstructure. That's why this is a kind of transformation strategy we usually try to promote. But what we need to draw your attention is with such a transformation strategy, you will not do too much on your temperature and time diagram. As you remember, this diagram was plotted by basically isothermal process. We take one temperature and we observe the phase transformation, and we gave this 3 points, 0, 50, and 100%, and we take another. So when you just use a continuous cooling transformation strategy, this will be not valid anymore, right? You will need to have another kind of points. And here I'm showing you the difference. So the dashed one, they're the so-called isothermal temperature and time curves. And the solid ones are this continuous cooling temperature and time curves. So you can see they differ a little bit, but more or less they're still following the same pattern. So now you can understand for this temperature and time diagram, you have basically 2 ways to draw it. One is by using continuous cooling transformation. This is why this diagram is also called the CCT diagram, CCT. But you can also do it via the isothermal transformation. In that case, we usually call it TTT diagram. But in the end, it is basically telling you the same thing. All right, so finally, we want to give you a sense of all these different phases and how they be different in terms of mechanical property. Now I'm trying to give you a comparison between the hypoeutectoid steel and the hypereutectoid steel. So both of them have pearlite. So I gave a mediate pearlite. So mediate means they're hard, but they're not so hard. They're mediate hard. And for the hypoeutectoid, you have the prior eutectoid ferrite, which is rather soft. And for the hypereutectoid steel, you have the pro-eutectoid cementite, which is hard. So now you can already imagine what will happen. So the driving force of the difference in terms of mechanical property for these 2 types of steels basically is the carbon content. Now, you probably remember carbon is gonna make your steel harder. That is related to our first strength hardening mechanism, which is called solution hardening, if you still remember what we learned in week number 2. That's why when you increase your carbon content in terms of the whole steel, you're increasing your strength, yield strength and tensile stress. So it basically goes up from hypo to hyper. So yield strength and tensile stress. The same applies to hardness. If you remember our correlation between hardness and tensile stress, so they're almost in a proportional relationship. And the consequences of all this increase of strength, of course, is falling down to the ductility, right? So your ductility will be decreasing with the content of carbon, so it decreases quite a lot for ductility and decrease even more for your impact energy, so the Charpy energy. So you decrease a lot in terms of that. That is the influence of the carbon content. And another difference in terms of microstructure is also on the grain size. Yeah, if you remember, we could get either fine perlite or coarse perlite by just control the temperature. If it's supercooling or if it's a lot supercooling or if it's a little supercooling. Yeah. So you also know what is the difference between fine and coarse grains, right? This is exactly what is happening. If you have fine grain, you will have, again, higher strength. And if you have fine strength grain, and the consequence of the higher strength is, of course, the reduction of your ductility. Yeah. That's the difference between fine and coarse perlite. So we can also compare the fine perlite with respect to martensite. So this is the curve you could see. Due to those features I have emphasized to you about martensite, you can see martensite is completely overshooting the hardness. So here I'm showing hardness, but you can imagine others. The fine perlite by magnitude also, by almost the magnitude. So you have much harder microstructure when you have martensite than fine perlite. Okay. And the last one is the so-called tempered martensite. So by tempering, we will learn a little bit more next lecture about how tempering is changing your microstructure. But you can also imagine by tempering, you're removing some internal stresses and you're also changing the microstructure. Basically, you're trying to create more soft alpha phase and also the cementite particles. And all of this is decreasing your strength, but it is increasing significantly your ductility. So this is here I'm showing you the reduction of area, which is one measure of the ductility. So that's why we're trying to always use this tempered martensite to get a balanced mechanical property in terms of both strengths. You see the strength is decreased, but not too much significant. But you get quite a lot increase in terms of ductility. All right, here I would like to give you a summary of our possible phase transformations. So we always start from austenite. By the way, I didn't speak about the mechanical property of austenite because it's usually at high temperature. But of course, you can imagine with a certain strategy, we can actually get austenite in room temperature as well. This is not covered at this stage of your study. You will see that in the future. Actually, austenite is a phase that you very much see in your cookware, because that is a stainless steel made in terms of austenite. But here we're speaking about austenite. We're starting from the normal iron carbon diagram where austenite is only stable at a very high temperature. And if we just apply a slow cooling, slow cooling, and also a less, let's say, a rather less supercooling, you will get a perlite phase, quite good, layered structure, and even coarse. But if you make rather faster, moderate cooling, you will actually reach the bainite, right? Because your supercooling is large and you get the status of bainite, which is the elongated cementite. So the bainite perlite, they don't differ too much in terms of kind of composition. It is more different from the morphology, right? So you will have still the alpha, but with the elongated cementite, not as beautiful as the layered structure. And if you make even faster cooling, so you get the quenching, let's say, then the final result is the diffusionless BCT martensite. But martensite is featuring very hard and very high strength, very poor ductility. We usually do a reheat and hold and cool down. That will give you the tempered martensite. So you will see how this tempering is done next lecture. But with the tempered martensite, you will get back some fine cementite particle plus alpha that will improve your mechanical property in terms of ductility. So here I'm giving you a summary slide also, yeah, the general trend, yeah, very general. This is not, everything is composition specific. So here is only a general trend. You have the strength ranked in terms of different phases, and also ductility, exactly the reverse of it. All right, I think that is all I want to speak about phase transformation. And I think we started with one equation to describe the rate of phase transformation. And I introduced you actually a little bit later, but I put it now before, two types of ways to conduct the phase transformation. And this is also corresponding to types of the fraction, the temperature and time diagram. So one is isothermal transformation, one is continuous cooling transformation. And applying those temperature time diagram, you kind of see four important phases related to their microstructure, and also some more phases. I gave you a general trend. All right, I think it is time for us to stop today's lecture. You probably noticed we have another chapter that I planned for you. Oh, I don't mean to end the whole screen sharing. But we will not have time to really go through that this week. So I would rather to put that in for the next week. Because I heard the voice from all of you, many of you, either from our feedback last week and also from your assignment, and also some individual emails. So thank you all for all this nice feedback that takes time for you to write. That's why we're making a little bit change of the course. So if you missed the first part of yesterday's lecture, I want to repeat today here. So first of all, you probably already noticed we slowed down a little bit, or even quite a lot, for you to take in the message rather in a good, let's say, rate. That's why we also slowed down in terms of the content I want to give you this week. Instead of 4 chapters, I gave you 3 only. So let me just delete this one because this is not given to you. That will be given next week. And that will decrease your working loads, I would say, quite significantly already. So if you still have problems, I really have to reevaluate, because this is a lot less. And assignment is what it is. What we changed also, in addition to the content, is we reduced the computational training. So we kind of put it into the optional as one strategy for those people who still would like to get the computational training. But that will be not incorporated into your assignment. So for those that wished on this, you should be happy now. Yeah. For this week, we will still have one computational training that will be provided you as a video. So you can choose to watch it. If you want to play with it, you can download the ThermoCalc to create those interesting phase diagrams. But as I said, it is optional. It is not reflected into your grading system anymore. And because we moved that, so that will also significantly reduce your working load in terms of exercise. For that reason, we also merged the Q&A time with the exercise. Because I didn't see many of you, only 1 or 2 students showed up during the Q&A. Maybe it's a better idea if you have more questions together. So we merged the exercise with the Q&A. So with that, I think you should be able to follow the lecture quite well and also conduct your assignments quite well. All right, I think this is the end of today. If you have any questions, please ask. Otherwise, I will see you next week, guys. By the way, we need to do a little bit of modification about our assignment 4, because there's one question is related to the chapter 11 of the textbook, and we will simply remove that. So if you have started the assignment, go ahead. Yeah, nothing will be changed in terms of 1, 2, 3, but the 4th one will be removed. So there will be an update about your assignment a little bit later today. So I see probably something is coming in chat, okay?